we're going to be thinking about the arc length of a circular arc. What does that mean? We're going to start off with just a circle. A circular arc is any portion of the circle of a fixed radius r where this thing traces out part of that circle. And that's what we mean by a circular arc. Now, circular arc will be, the word is subtended by an angle theta. That tells you sort of the angle, this interior angle right there. This is called a central angle if you want to be super specific about that. So anyway, the question is, how long is that length of arc if we have some angle theta here on some circle of radius r? Now, there are two approaches to this. The first approach is going to be, we're just going to use some logic and basic deductive reasoning to get there. And the second way is going to be a more formal mathematical way of looking at it. So using logic, let's sort of think about this. We know that the entire circle is going to have a length, an arc length of 2 pi r. That's because that is what's known as the circumference. The circumference is the distance going all the way around the circle. And so let's say we have an angle theta here. Well, if we're working in degrees, this theta is going to be some measure, let's just say, I don't know, maybe 60 degrees or whatever. But if we think about it, this is a proportion of the whole circle. So if this were 60 degrees, it would be 60 degrees out of the possible 360 degrees to go all the way around. And so for the arc length in radians, or excuse me, in degrees, what we're going to have is going to be this angle divided by 360. So it's going to be this fraction of the whole circle, or this proportion of the whole circle. I'm going to put degrees here. And so when you do some simplification, the 2 is going to reduce 360. You're going to have theta times pi times r over 180 degrees. And this is the formula that we use when we're in degrees. Now, you can see that this formula, it doesn't look particularly nice. It's just, it's kind of messy. It's got a fraction in it, and it's got 180 degrees in the denominator. Let's do this again in radians and see what happens. So, just as before, circumference is still the whole same thing. But now, instead of thinking about theta in degrees, we're going to think about theta in radians. This is theta out of a possible 2 pi radians to go all the way around. So the proportion this time is going to be theta out of 2 pi. And then we're going to multiply this by 2 pi r, just as we did here, because this is the distance going around the whole thing. So you have a proportion of the whole circle. And now this time when we reduce, the 2 pi's cancel out, and this gives us a nice formula. S is equal to theta times r. And so this gives us the arc length given an angle either in degrees or in radians. This gives us the length of the arc subtended by that central angle. Now this formula right here is actually really close to the mathematical definition, the mathematical approach. You might recall that we defined the angle in radians to be theta is equal to s over r, where s was the arc length and r was the radius. And we said theta was defined by this value. And if you just rearrange this, multiply both sides by the r, you get r times theta is equal to s, which is exactly this formula down here. And so this kind of shows us how the mathematical approach makes things a lot easier. We set ourselves up with a good definition of what an angle is. And because of that, we have a nice formula for what the arc length is. And all it is just a rearrangement of this formula. So here's an example of a problem that uses arc length. The high roller at the link has a radius of 260 feet. How far has a cart traveled if it rotates 30 degrees? So for those of you who don't know, the high roller is the Ferris wheel on the Las Vegas Strip. Has a radius of 260 feet. And this thing is going to rotate 30 degrees. Now, it doesn't matter where it starts because the circle is the same all the way around. So we're going to start wherever I drew this thing, and we're going to say it's going to rotate by 30 degrees. And the question is, how far has it physically traveled as it moves along that arc? We're going to look at this problem in a couple different ways. We're going to start off by using just the formula. So formula for arc length. When we have arc length in degrees, this is going to be theta over 180 degrees times pi times the radius. And so you can see we just plop the numbers in. So this is going to be 30 degrees over 180 degrees times pi times 260. Now, there's not a lot that we can do here. We can reduce some fractions. So this reduces to a 1/6, and we can try to reduce it with the 260. This turns out to be divisible by 2, but not 3. So 260 over 6 is going to be 130 over, it's going to be 1/6. So 130 over 3 pi. Now, this number by itself isn't great to use. If you tell someone 130 pi, they're not going to know what that is. We can do a little bit of work by just trying to simplify this a little bit. So if we reduce the fraction or write it as an improper fraction, we can see that this is going to be something like 43 1/3 times pi. But that still isn't a great value. We would like to know what this thing is, because when we measure physical units, we tend to want to have some sort of strict, some sort of numerical value here. And so if we can plug this into a formula, or plug this into a calculator, we'll get the number 136.13, and this will be in feet. So this way of approaching it is just plug into the formula, don't think, just plug in and go, and you'll get this value down here. What are other ways of looking at this that may help build our intuition? Well, first of all, one thing we need to do is build intuition with radians. And so we can think of this and convert this to radians. 30 degrees is the same as pi over 6, and then use the radian formula, which is S is equal to theta times R. This right here, this is going to be, we said 30 degrees is pi over 6 radians, so pi over 6 times 260. And if we actually do this calculation here, that's exactly the same values we got here. It's just that we didn't have as much reducing to do with the fractions and so forth. We still have to work from here and get the rest of the way. But at least in this first step, we have a simpler looking fraction. We can also think of this 30 degrees as being 30 degrees out of a total of 360 degrees. So this is 30 degrees over 360 degrees, which is, well, not about, this is 1/12. And so we can say, well, we want 1/12 of the distance going around the circle. And so that use that fraction there instead of this reduced form. It's sort of a little bit more, builds a little bit more of the intuition. A similar idea is the area of the sector of a circle. Now, what is a sector of a circle? Well, the sector of a circle, if we think about cutting out a wedge, almost like a pie-shaped wedge, this right here is a sector of a circle where this is at the center. And so the area of this thing is the area of this pie-shaped wedge that we have right here. We're going to look at this the same way as we looked at the other example, which is we're going to think about this as proportions. We know that the area of the entire circle is area is equal to pi r squared. So what happens? Let's say that this is an angle theta. Let's label this radius r. And so if we use the same proportion, for the area of the sector, I'm going to write A sub S, area of the sector. This area is going to be equal to, well, we're going to use a proportion of the whole circle. So we'll start with degrees as before. So theta over 360 degrees times pi r squared, right? So again, a proportion of the area of the circle, and that proportion is measured out by this angle here. If we did it in radians, this would be theta over 2 pi times pi r squared. And again, you'll notice that because this pi appears here and here, that this reduces, and this gives us a nicer formula for the area of a sector when we're dealing in radians compared to when we're doing it with degrees. In degrees, we're stuck with this 360 degrees in the denominator. This one's just theta over 2. It's a little bit nicer, but the pi's go away. Here's an example looking at the area of the sector of a circle. A lawn sprinkler sprays a distance of 20 feet and rotates through an angle of 60 degrees. What is the area of the sector of grass the sprinkler waters? So here we have a sprinkler head that's going to turn back and forth between these two angles. It's going to be a 60-degree angle here. And we're interested in the area of this sector, and this has a radius of 20 feet. Now, once again, we could use either formula, but this time we're going to sort of focus on the radian value, because that's the one that's going to take more practice, because otherwise we're just plugging this into a formula and not really thinking. So what is the area of the sector? So the area of the sector when we have radians is theta over 2 r squared. Let's think about 60 degrees. Now for 60 degrees, that you could go back to the unit circle picture and see what it is, or we could just sort of think about it. And I'm going to practice the thinking process. The key value to remember is that 30 degrees is pi over 6. And so if we have 60 degrees, that's 2 times 30. 2 pi over 6 is the same as pi over 3. And so this is equal to pi over 3 over 2 r squared. Now fraction inside a fraction, you have to multiply by the reciprocal, so this is going to be pi over 3 times 1/2 r squared. The r value is this 20 feet right here, and so actually let me put that in right here. 20 squared is 400. So now we have to multiply this out and see what we get. So the 2 reduces with the 400 gives you 200. We get 200 pi over 3, which again, this isn't so helpful in a practical problem because no one looks at that and immediately can say, oh, I shouldn't say no one can, but typically when people are given a number like that, they don't know what area that actually represents. And so what we need to do is we need to plug this into a calculator. And if we plug it into a calculator, put the answer over here, you get the answer 209.44 square feet. And so this sprinkler sprinkles an area of almost 210 square feet.